Okay, in this video I want to talk about the complex numbers proper here. The complex numbers are numbers of this form, a plus bi, where of course I is what? I is the square root of negative 1 that we discussed in the previous video. Okay, a and b are real numbers, okay? All numbers of this type are called complex numbers, okay? We sometimes denote the complex numbers by cap C, okay? Let me first of all mention that every real number is also considered to be a complex number. So for example, let's say I had the number 7. I could actually consider that to be a complex number where I've got 7 is equal to 7 plus 0i, okay? Now remember that 0 times any number is 0, right? That still holds for complex numbers also. So 0 times I is actually 0. 7 plus 0 is 7, okay? I put a dot between 0 and I like I usually do because otherwise it looks like oi. Anyways, thus the complex numbers are could be considered an extension of the real numbers, okay? All right. In a plus bi, a is sometimes called the real part, okay? And b is sometimes called the imaginary part. Though when we're talking about b, remember b is actually a real number, but it's the coefficient on I. Now, by the way, sometimes other people will mention this whole thing, this whole bi part to be the imaginary part, which makes more sense to me, but that's the way it is. Okay, so a is the real part and b is the imaginary part, though the coefficients a and b are both real numbers. Okay, let's look at some more examples here. We already had this one. 7 is 7 plus 0i, showing that every real number is also a complex number. A pure imaginary number here, 3i is 0 plus 3i. So if you forced a real part onto it, you could do that. It's kind of a waste of time usually, but we would go 0 plus 3i if somebody asked us to. 2 plus 3i, that would be a complex number with what? Real part 2 and imaginary part 3. 5 minus pi I, this would have what? A real part of the square root of 5 and an imaginary part being negative pi. By the way, when we say that the complex numbers have the form a plus bi, really they can also have the form a minus bi. Okay? So instead of going square root of 5 plus negative pi I, we could do that. It's easier to just go square root of 5 minus pi I. Anyways, these are all complex numbers, just examples. Let's talk about the arithmetic of complex numbers. Addition and subtraction of complex numbers. Okay, how do you do that? It's treated just like you would polynomials in the variable I, okay? Now you should know how to add polynomials and multiply polynomials and stuff, okay? Let's add these polynomials. So add them like they were polynomials in I. 3 plus 2i plus 7 minus 5i. Okay, what do you do? When you add these, you just combine the like terms. 3 and 7 is 10, okay? 2i plus negative 5i is adding negative 3i, better written as minus 3i. So our final answer in this case would be 10 minus 3i, okay? Very simple. Basically, if you've seen one, you've seen them all. Let's do an example of a subtraction here. I've got 3 plus 2i minus 7 minus 5i. Again, treat it just like you would a polynomials in I. And combine like terms. Don't forget you're subtracting this time. So the real parts, 3 minus 7, that's negative 4. 2 minus negative 5 is plus 7. So we've got plus 7i. Okay, very easy, simple. If you get your real arithmetic correct, then you're in good shape. Multiplication, again, multiplication of complex numbers is treated like multiplying polynomials in I, but the major thing to remember is that I squared is what? Is reduced to negative 1. I squared is negative 1. So we're not going to leave any higher power on I than the first power. Because you remember all powers of I that we saw in the last video, all integral powers anyway, end up being what? 1, -1, I, or negative I. Not necessarily in that order the way I've written it, or said it. Okay, let's just go ahead and do this. Let's go 2 plus 7i times 3 minus 4i. I'm going to multiply these. Just FOIL it out. Okay, so 2 multiplies on the 3, I get 6. 2 multiplies on the -4i, I've got -8i. Yes, we've got all those same properties, the distributive property, the associative property, and everything, just like we had with the real numbers. So this is very easy here. Okay, so you can change the order on the products and stuff like this, because multiplication is commutative here. Let's do this. 7i times 3. Let's put the 7 and the 3 together and we get 21i. Don't forget that there's a plus there, right? So you're adding. So it's plus 21i. And now here I'm going to do this. Negative times, or I should say a positive times a negative is negative. 7 times 4 is 28. I times I is I squared, right? Okay, but here I'm jumping in here. Remember, I squared is -1, so I'm replacing I squared by -1 here. I'm going to combine these two I terms here. -8i plus 21i is plus 13i. Okay, so we've got 6 plus 13i minus 28 times -1. Okay, the double negative becomes positive, so it's like adding 28. That's a like term with 6, right? Because it's just a term involving real numbers and not I. 6 plus 28 is 34. So the answer is 34 plus 13i. Okay? Okay, so just FOIL it out. Remember, I squared is -1. Combine like terms. Okay? Let's go ahead and look at this. 1 plus 2i times 2 plus 13i. 1 times 2 is 2. 1 times 13i is 13i. So we got those first two terms. 2i times 2 should be plus 4i, right? Okay. 2i times 13i should be 26i squared. Okay. Now students, when they get really fast, may automatically jump down to what I did here and go to -26 because we know I squared is in fact -1. 13i plus 4i is 17i. So we've got 2 minus 26. We got -24 plus 17i. Okay. By the way, like we said originally, when we define these, okay, the real part comes first and the imaginary part comes second. That's just our tradition. So we go -24 plus 17i for our final answers. Box in your final answer. Okay, here's an interesting one I want to do. I want to go 2 plus 3i times 2 minus 3i. Now you notice these two complex numbers differ in a very simple way. One has addition between the terms, and the second one has subtraction between the terms. Otherwise, they're identical, right? Now, when I multiply these, again, just FOIL it out. 2 times 2 is 4. 2 times -3i is -6i. 3i times 2i, or 3i times 2 is plus 6i. Negative times positive is negative, so we got a negative there. 3 times 3 is 9. I times I is I squared there. So that actually becomes positive 9, doesn't it? Notice that the I terms cancel out, okay? Okay? Those would be the cross terms in this thing, and they have opposite signs, so they cancel out. So we actually get what 4 and 9 is 13, okay? Notice that 13, I'm not going to write it 13 plus 0i, by the way. That's a positive real number, okay? All right, and we're going to see this type of thing happening in each case when you've got a number times what its close associate here calls its conjugate. Okay, so more on this in just a minute. There's another operation here which does not exist in the real numbers because it's trivial for the real numbers. It's conjugation. The conjugate of a plus bi, written a plus bi with a big bar over the whole thing, okay, that's in case you don't know what the a and b actually are, is the complex number a minus bi. So to take the complement of a complex number, you just change the sign on the imaginary part. Okay? So here, this would be read as what? The conjugate, because of the bar, the conjugate of 3 minus 7i, and that would equal what? Just change the sign on the imaginary part? 3 plus 7i. Okay? Here I've got the conjugate of 27i, okay? Do you see I'm going to change the sign on the imaginary part? The imaginary part is what? The 27 on the 27i. So that becomes what? Negative 27i. I should be boxing in my final answers, huh? Okay, there it is. Alrighty. How about the conjugate of 13? 13 is a real number. Let me throw this in here. I could consider 13 to be 13 plus 0i, and then I'm taking its conjugate. That would be 13 minus 0i. 0i is still 0, so it's still 13. And you can see there's nothing special about 13 here other than it's a real number. So the conjugate of any real number is just that same real number back. Conjugation doesn't change real numbers, okay? Conjugation does not change real numbers. Okay, now let's talk about this situation that we had up here in greater generality. Multiplying a complex number by its conjugate. Okay, suppose that this is not a zero number. Okay, now it could actually be zero here, but I'm going to assume it's non-zero here in this following statement I'm going to make here. Suppose I've got that complex number a plus bi, and I multiply it by its conjugate a minus bi. Okay, just foiling it out. A times a, I've got a squared. A times negative bi, I get negative abi. When I go plus bi multiplies on a, I've got plus. I've decided to write ab instead of ba on my I. Okay, it won't matter, right? Those are product of two real numbers, and that's commutative. Okay, plus times minus is minus, so I've got a minus here. B times b is b squared. I times I is I squared, so we've got this. Notice that these clearly, the I terms cancel out, okay? So this is just like that other example we did on the previous page, okay? And then I squared is negative 1, so I've really got a squared plus b squared, which is a positive real number since this thing, either a or b is not 0, right? Okay, so this has got to end up being a positive real number here. That's a sum of squares of two real numbers, at least one of it, which is non-zero. So that's going to be a positive real number here. Okay, this is a formula you want to remember. Okay, the sum of squares can be factored now. That's another way to think of it, which you couldn't do in previous classes. But a plus bi times a minus bi is a squared plus b squared. Okay, so that's going to be a real number there. Okay, and in fact, if neither of these, if this isn't the 0 here, then it's going to be a positive real number. Okay, all right. Now remember, a and b are real numbers, so you're taking the sum of the square of two real numbers. Okay, let's take an example. 2 plus 3i times 2 minus 3i. I'll have a equals 2 and b equals 3, so it's going to be 2 squared plus 3 squared. Without going through this stuff up here. Okay, I'm not going to go through all that. This is easier and quicker than that now. I know it's 2 squared plus 3 squared. Okay, what's that? 13. How about 3 minus 5i times 3 plus 5i? Okay, I could have a equals 3 and b equals negative 5. But since I'm squaring, I might as well make it what? Positive 5. So it's 3 squared plus 5 squared. Okay, what is that? That's 9 and 25 is 34. Okay, alrighty. All right. By the way, this is an exercise for you. Okay, all right. The conjugate of the product of two complex numbers is the product of their conjugates. Now I'm going to use that fact here in a little while. Okay. Oh, one other thing I forgot to throw in here that I really should here. Some people talk about the absolute value or even the magnitude of a complex number like this. 3 minus 5i. Okay. 3 minus 5i. Okay. What this is the square root of this thing right up here. The complex number times its conjugate. Okay. So in this case, it would be the square root of 34. Okay. So that would be its absolute value. By the way, if I did this, the square root of, or the absolute value of 3 plus 0i, this would be what? The square root of 3 plus 0i times 3 minus 0i. Okay. I guess I wrote it away there. And you can see that's the square root of 9, which is 3 again. Okay? If I made this negative 3, I would have negatives in here. It's still going to end up being, what, 3. Okay? This is the absolute value. This is a generalization of the idea of absolute value to complex numbers. Okay? Alrighty? Let's talk about division of complex numbers. Dividing a complex number by a real number. Okay? Let's do this first. Suppose I have this complex number 3 plus 5i, or 7i, not 5i, 3 plus 7i divided by 5. Okay? And I want to write the answer in the form a plus bi or a minus bi. So don't just leave it this way. It's going to be very simple. You're just going to use the distributive property. So it's 1/5 of 3 or 3/5 plus 1/5 of 7i, which is 7/5 I. Ta-dum. So in other words, the 5 will just divide into both terms there. Okay? Now it's in the form a plus or a minus bi. Okay? Now let's do so. Now keep this in mind because we're going to actually use this little factoid here in a minute. Dividing a complex number by an imaginary number. And what I mean by imaginary number is a non-real complex number. Okay? So a complex number with a non-zero imaginary part. Okay? Well, let's just take this example. Suppose I go 3 plus 7i divided by 2 minus 5i. Now you need to remember this trick because you're going to get tested on it. Here's what you do. You multiply this. You just write it down again here. You multiply it by a fancy form of 1. Now if I multiply something by 1, that leaves it unchanged, right? Now what is that fancy form of 1 that'll help me out here to actually get my answer? The fancy form of 1 I want to take is I want to come over and look at the denominator. The denominator is 2 minus 5i. Okay? Now take that, the conjugate, yes, conjugate of that denominator and divide it by itself. Well, the conjugate of that denominator is 2 plus 5i, right? I'm going to take 2 plus 5i and divide it by itself. That ought to be 1, right? 2 plus 5i divided by itself ought to be 1. It is, since 1 times 2 times 5i is 2 plus 5i. So I'm just multiplying by what? 1. So that should keep that equal sign there valid, right? That should be a valid equal sign. Okay? But what's the advantage in doing this? Well, you know that multiplying fractions, even with real numbers or complex numbers, it's easy. All you do is multiply straight across. You don't have to look for a least common denominator or anything like that. Okay? You just multiply straight across. So it's numerator times numerator over denominator times denominator. Now we'll consider the numerator here in a second. I really want to focus on the denominator right now because this is the key of why I'm multiplying the denominator times its conjugate. Because when I go that denominator times its conjugate, I get a real, positive real number value on the bottom. Remember that we showed up here previously that what? A complex number times its conjugate gives you the sum of the square of two real numbers, which if they're not zero is a positive real number. And if I'm dividing by a positive real number, it looks like this case just right above. Okay? Alrighty, so this is what we're doing. So it's actually what? Now remember, 2 minus 5i times 2 plus 5i is going to be easy, right? 2 squared plus 5 squared. No negatives, no i's or anything. 2 squared plus 5 squared. It's the a squared plus the b squared. Okay? All right? Now, all I did in the numerator was FOIL. I didn't write every little detail here on this. But if you multiply the numerators together, you will get negative 29 plus 29i. Okay? Now, if you actually compute that denominator, it's 29 also. So that 29 is going to divide both the real part and the imaginary part here. So I'm going to get negative 29 over 29, which is negative 1, plus 29 over 29, which reduces to 1i. Okay, so the answer is -1 plus I, and we've got it. Okay, so that's the trick. Multiply by what? A fancy form of 1 being the conjugate of the denominator over itself. Let's do another one. Okay, let's go 1 plus 7i divided by 2 minus 3i. Okay, what's the conjugate of the denominator? That's 2 plus 3i, so divide that by itself. So understand what you're doing at each stage. You're multiplying by 1. Okay, that should leave the value unchanged. So that should be a valid equal sign. Let's go ahead and multiply the denominators together to get first. That should be what? 2 squared plus 3 squared. Okay, positive real numbers, no negatives, no i's. That's actually 13. I wrote this wrong here and then wrote over it and it looked kind of ugly, but there it is. Okay, I actually FOILed out the numerator, multiplied it out, and I think I got it right. I think I got -19 plus 17i, and I'm dividing that by what? 2 squared plus 3 squared is 13. Okay, so I've got -19 thirteenths plus 17 thirteenths I for my final answer. Okay, let's talk about negative powers of I now. Remember, I promised to do that in the previous video. Okay, just real quickly here. If I was to take I to the -13 power, okay, I would consider that 1 over I to the 13th power. Remember, a negative exponent has the effect of just making it reciprocal, right? So I would go 1 over I to the 13th power. Now, here's where I'm going to pull in some facts that I've mentioned, but I haven't really used yet. I would take the conjugate of the denominator over itself. Now, the denominator is I to the 13th power. If I was to go I to the 13th power and take its conjugate, I claim, because that's a product of a bunch of complex numbers. Do you remember I had as an exercise above EFY? That's actually the conjugate of I raised to the 13th power, okay? And that's what I've written here. Now, what's the conjugate of I? It's -I, right? Okay, just change the sign on the imaginary part. So this is actually what? It's 1 times -I to the 13th power divided by what? I to the 13th times -I to the 13th. Because both of these terms have the same exponent, I can factor that 13th out of both of them, and I'm going, well, so to speak, not really factoring it out. Anyways, I can write this. I times -I. I times -I, though, if you work it out, is actually 1. Okay, so that's 1 to the 13th power. Any power of 1 is 1. So I've actually got -1 to the 13th power. Okay, now, because I'm raising it to an odd power, negative to the 13th is negative. Okay, then I've got I to the 13th power, and you know how to find I to the 13th power from the previous video. You just find its remainder upon division by 4. 13 divided by 4 has a remainder of 1. So it's -I to the first is -I. Okay? So in general, following this same reasoning, not just 13? If I'm going I to the -n, that's the same as -I to the n. And then you should be able to figure that out from there. Okay? Alrighty? Alright, well, I hope you understood all that stuff.